What you're seeing here is the poristic family of triangles, the blue ones. The blue triangles, if I animate them, these blue triangles here, they have a fixed incircle centered at x1, and their vertices lie on a fixed circumcircle, this purple circle here, centered on x3. So this is a well-known, well-studied family. What we're going to be doing here is study not only this family, the family of blue triangles, but the family of Simson lines. These Simson lines, so let's take a point P, or sorry, a point Q, shown here blue, on anywhere on the circumcircle of the poristic triangle. So I can actually vary the position of point Q there. I can vary that, and I can consider the Simson line from Q onto the blue triangle. The Simson line, the current Simson line, is defined by these 3 points, which are perpendiculars dropped from Q onto the 3 sides of the blue triangle. So it's well known that if Q lies on the circumcircle of a triangle, these 3 perpendiculars are collinear. So I'm showing the Simson line right here as a dashed blue line. And what's remarkable is that as I slide through the family of blue poristic triangles, the family of Simson lines with respect to Q onto the poristic triangles is turning about a point Q prime, a fixed point Q prime, i.e. the envelope of Simson lines is a point, since the center of rotation of this line family is a fixed point Q prime. Interestingly, if I move Q around on the circumcircle, this Q prime point is going to move on this dashed elliptic locus. So if I move the point Q around, you can track Q prime there moving on that elliptic locus. Let's move it really slow. So I'm just varying Q here, and my point Q prime, which is the envelope of Simson lines over the poristic family, the center of those lines, or the envelope, which is just a point, is moving as well. So let's leave Q over here, and let's go ahead and focus on the set of dash blue Simson lines once again. All right, so a connected phenomenon is if I draw the associated green excentral triangle to the set of poristic triangles. These excentral triangles are known to have vertices which ride on a circle, on a fixed circle, which is centered on the fixed circumcenter of the set of excentral triangles, x3 or x40. So the circumcenter of the excentral is x40 of the reference triangle. So here's x40. And here's the circle of radius 2 big R, where R is the circumradius of the poristic. So the locus of the vertices of the excentral is a circle of radius 2R, 2 times the circumradius of the poristics, centered on x4. So I can follow my my excentral triangles to the poristic family. I can see indeed that their vertices follow this nice 2R circumcircle. Now here's 2 phenomena that I'm showing simultaneously. Let's go back to now choosing a point P, no longer Q, but a point P on the circumcircle of the excentrals. It turns out, so I can move this point P around, okay, as I wish, this point P here. It turns out that again we have a similar phenomenon in that as I vary my poristic family and I drop 3 perpendiculars from P to the excentral triangle to the poristics, I'm going to get these 3 green points. Here's one, here's a second one, and here's a third one. So this is the Simson line of the excentral family with respect to a point P on the circumcircle. Here's the line. Now again I have the same phenomenon. This family of lines, as I vary my poristic family, is also rotating about a point. Now this point P prime on this case happens to lie on the circumcircle of the poristics. So here's my set of Simson lines, the dashed green ones, rotating about a point P prime, which lies on the circumcircle of the poristics. Now notice that P connected to P prime is collinear with the incenter. So that's a nice property. If I vary the position of P, I get the collinearity. Okay, so I can put, for example, P down here. Here's my center of the Simson lines, i.e. the envelope of the Simson lines is also a point, and this point is collinear with x1. Now, interestingly, if I parameterize P as being by an angle u, so I have the cosine u, sine u with respect to this point x40, it turns out that P prime, the point-like envelope of the Simson lines, coincides with point Q parameterized on the circumcircle with the same angle with respect to its center x3. So if P is a point cosine u, sine u with respect to its center x40, P prime coincides with the point Q, which is also cosine u, sine u with respect to x3, the center. All right. Now, again, before I was observing the locus of envelopes of the Simson lines of the poristics, these Q primes, they actually moved along an ellipse as a varied Q. If I vary P, that envelope, that point-like envelope, P prime of the Simson lines with respect to the excentrals, moves along a circle, right? So if I vary P, my point Q prime is moving along a circle, and that circle is the circumcircle of the poristics. Very nice. Okay, so let's animate that again. You can see here that these Simson lines are also rotating instantaneously about a fixed point. So it's remarkable that the family of Simson lines of a point on this large, on the circumcircle of the excentrals is a point on the circumcircle of the original poristic family, and the envelope of Simson lines of a point Q on the circumcircle is also a point. Okay, so that's pretty remarkable. Now, there's a third phenomenon, a third object that I'm drawing here, which is this large red deltoid. Now, you will remark, so this is the Steiner deltoid of the points lying on this orange circumcircle with respect to the excentral triangle. Okay, so we know that if I place a point anywhere on its circumcircle, okay, the feet of the petals are going to be collinear, so they're going to form Simson line. So here's a Simson line. Now the envelope of these Simson lines, if I maintain my excentral triangle fixed, and I just consider the envelope of these Simson lines as a very P across the circumcircle of the excentrals, this is going to sweep out these curves are going to sweep out this red deltoid. Now, what's remarkable about this deltoid is that it is just rigidly rotating about x3, since the quote-unquote internally tangent, I was going to call it the incircle, but the internally tangent circle to the deltoid is a circle of 9 points, the Euler circle. Well, the circle of 9 points of the excentral triangle is congruent with the circumcircle of the reference triangle. So the family of excentral triangles to the poristics has a fixed circle of 9 points, meaning that this Steiner deltoid has a fixed internally tangent circle, meaning that the family of Steiner deltoids is rigidly rotating about this 9-point circle. How do I know it's not changing its size? I know that because the area of the deltoid is half that of the circumcircle of the excentrals, and the circumcircle of the excentrals, this orange circle, is not moving. So this deltoid is not changing shape at all as it rotates. It's rotating about x3, and its internally tangent circle is also fixed, is the circle, the Euler circle, or the circle of 9 points of the excentrals, i.e. the circumcircle of the poristic family. So here you have these three phenomena. Let's recap them. I have a point-like envelope for the Steiner or for the Simson lines of the poristic triangles with respect to a fixed point Q on the boundary, on the circumcircle. I also have a fixed envelope for the Simson lines of the excentral triangle with respect to a point on its circumcircle. And I have a rigidly rotating Steiner deltoid of the excentral triangles with respect to all points on its circumcircle.